All right, let's dive straight into this explainer. We're tackling EPA Method 7E today, and we're going to treat this dense, highly technical regulation as your ultimate field manual for measuring nitrogen oxides, or NOx, in stationary source emissions. Look, this method is the absolute gold standard in the industry, but reading it can honestly feel like trying to decipher ancient hieroglyphs. So today, we're breaking it down together. We're translating all that regulatory jargon into a clear, actionable narrative, going step by step so you understand exactly how to collect unassailable, compliant data.
Here is our game plan for today. First, we'll cover the goal of Method 7E. Second, the anatomy of the analyzer. Third, the pre-test checkup. Fourth, running the emission test. And fifth, validating your data. We're going to follow a stack gas sample right from its source inside the chimney, straight through our analytical VIP pipeline, and all the way to validating the undeniable mathematical data it produces.
Section 1. The goal of Method 7E, understanding what we measure. Because before we build our system or even think about sticking a probe into a smokestack, we really need to understand exactly what we're hunting. What is our target analyte, and why are the rules around capturing it so incredibly strict?
Well, according to the method, NOx is defined as the sum of nitric oxide and nitrogen dioxide in the effluent gas. So the crucial point here is that while we are measuring NOx as a whole, Method 7E specifically requires us to convert that nitric oxide and measure the entire sample as NO2. This guarantees data accuracy. Your analyzer needs to be calibrated specifically for these species to ensure literally nothing slips through the cracks. But why do we care so much about this specific compound? It comes down to the sheer gravity of what you are doing as a tester. Section 5.0 of the method spells it out point blank. A concentration of just 200 parts per million can be fatal. It causes edema in the lungs that might go totally unnoticed for days. So this isn't just bureaucratic red tape or mindless box checking. Absolute accuracy in Method 7E isn't just about environmental compliance, it is fundamentally about immediate human safety. And that is the why behind every single strict rule we're about to cover.
Moving to Section 2, Anatomy of the Analyzer, Building the VIP Pipeline. Now that we know the stakes and just how hazardous this gas is, let's construct the specialized measurement system we need to safely transport and analyze the sample without accidentally altering its chemical makeup. A huge part of this VIP pipeline is the above dew point zone. This is absolutely critical. The sample temperature has got to be maintained at a sufficiently high level, all the way from the probe through the filter to prevent any condensation before it reaches your moisture removal equipment. Think about it. If water condenses, it can dissolve the NO2, effectively scrubbing your sample and giving you a falsely low reading. You'd essentially be reporting clean air while highly toxic gas is actually escaping. To prevent that disaster, you must strictly maintain a very specific sequence. First, pull the sample using a non-reactive probe made of glass, stainless steel, or Teflon. Second, pass it through a heated particulate filter to strip out the soot without dropping the temperature. Third, keep it heated as it travels down the sample transport line. And finally, deliver it securely to the NOx gas analyzer. Every single component here must be inert so it doesn't react with the gas you're sampling.
All right, Section 3, the pre-test checkup, the warm-up routine. Okay, your system is built, but before you collect a single sample, your system must rigorously prove its accuracy to you.
The EPA provides a testing flowchart that acts as your actual roadmap in the field, ensuring you never skip a required QA/QC step. But hey, real quick before we go deeper into these exact steps, I've noticed a lot of folks aren't liking or subscribing to the explainer lately. I really need your support to motivate me to keep making these, because let's be real, you will not find a more detailed EPA method breakdown anywhere else on the internet. I'm providing all this for you, so please hit like, subscribe, and also make sure to send me an email for QSTI exam preparation. Okay, back to the roadmap. Method 7E does not forgive mistakes. If you fail a check, you do not proceed. You stop, you fix it, and you start the sequence completely over. You literally have to pass every single one of these checks before you can even think about starting. You verify your calibration gas certificates to ensure they meet the EPA traceability protocol. You run an analyzer calibration error test. You absolutely must prove your NO2 to NO converter efficiency is at least 90%. Then comes an initial system bias check, a system response time test to figure out how long a sample takes to travel your VIP pipeline, and an interference check to guarantee other gases like CO2 or SO2 aren't tricking your analyzer.
Now this is where people get tripped up all the time, the difference between analyzer calibration error and system bias. Calibration error checks just the brain of your setup by shooting gas directly into the back of the analyzer.
But system bias, that tests the integrity of your entire VIP pipeline. You inject the gas way up at the probe tip, so it has to travel through the filter, down the heated line, and through the conditioner. If your system bias fails, you know for sure you have a leak or a reactive component somewhere in your line. Which brings us to Section 4, running the emission test, collecting valid samples. With all of our rigorous calibrations passed and documented, we can finally insert the probe into the stack to run the actual test. But of course, we can't just stick it anywhere and hope for the best. Unless your stack is extremely small, like less than 4 inches in diameter, you first have to do a stratification test. Think of a poorly stirred cup of coffee where all the sugar sits at the bottom. Gases do the exact same thing in a stack. The stratification test tells you if the gases are mixed well enough to sample from just one single centroidal point, or if you need a 3-point traverse, or if they're highly stratified, meaning you've got to move your probe across 12 different traverse points to get a truly accurate average. Once you actually begin your test run at those traverse points, pacing is everything. You're required to record at least one valid data point per minute to stay in compliance. This ensures you're continuously monitoring any fluctuations in the effluent gas, giving you a highly granular picture of what is actually leaving that stack over the duration of the test. And there is an absolute limit you cannot cross. We call this the golden rule of Method 7E. Your calibration span is the upper limit of your analyzer's calibration, which is set by your high-level calibration gas. If your average emission readings spike higher than that high-level gas, boom, that run is instantly invalid. You just cannot report data that falls outside the bracket of what you've actively proven your machine can accurately measure. You'd have to recalibrate with a higher span gas and do the whole run all over again. Section 5. Validating your data. Mathematical proof. So you've completed your test run, you've collected your 1-minute averages, and the equipment ran perfectly. But as a tester, your job isn't quite done until the math holds up to EPA scrutiny. We still have to mathematically prove the system didn't drift while it was working. And you are held to incredibly strict tolerances here. Your initial analyzer calibration must be within 2% of your calibration span. Your system bias from the probe cannot deviate by more than 5%. And over the course of your test run, your drift, which is the change in your system's reading from the start of the run to the end, cannot exceed 3%. Think about that. If you chose a calibration span of 100 parts per million, a 3% drift gives you a tiny 3 ppm window forgiveness. To prove you actually stayed within that 3% window, immediately after the run ends, you have to inject your low-level and upscale calibration gases right back into the system. The catch? You must do this without touching or adjusting the system in any way whatsoever. You're measuring exactly how much the instrument drifted from reality while measuring the stack. If it fails this post-run bias check, you throw out all the data from that entire run, no exceptions. As we wrap this up, I want to leave you with one final thought. We've spent this explainer diving into heated lines, calibration spans, and really rigid post-run math. But zoom out for a second. Given the deadly toxicity of NO2 that we talked about at the very beginning, your strict adherence to this incredibly specific procedure isn't just about passing a random audit. As you master this field manual, remember that your precision, your refusal to cut corners, and your absolute dedication to the math directly protects the air that we all breathe. Thanks for tuning in, and I'll catch you in the next explainer.